Hello, today we are continuing our study of mechanics and we are going to look at another type of motion that we haven't talked about until now, rotational motion. In mechanics there are two types of motion that we always talk about, translational motion and rotational motion. In translational motion we know that all the points of a given body will follow the same trajectory, so there's no rotation of those points. But respectively, of course, in the task and in life, we always meet with situations when an object starts to rotate. For example, you can sit on a Ferris wheel, and in this case, you will move on a circle, making a certain rotational motion. Or, for example, moving on an automobile and entering some turn, you too will move along some arc of a circle. So each of these motions will be described by its own parameters, and of course it's very important to understand how it will be related to the translational motion, because we have these two motions very often. That we have these two movements very often together. Let us remember an elementary wheel that rolls on the road. That is, in this case, the wheel will participate in two motions simultaneously. This is the forward motion of the whole wheel forward and the rotational motion around its axis. Therefore, in order to correctly describe the motions of such objects, we must clearly understand how the translational motion is described and how the rotational motion is described. So in terms of rotational motion, we can study it by looking at the rotation of some objects in this case. Such an object can be some disk that moves at a certain speed, that is, rotates by some angle in some time. Why in this case it is inconvenient to describe the rotation of such a disk using standard linear parameters. Such parameters, for example, are linear velocity. If you and I look closely at different points on this disk that are at different distances from its axis of rotation, let's say it's moving in this direction, then the point that's on the edge of this disk has a velocity that is tangential to its trajectory, that is perpendicular to the radius that we have drawn to this point. It will be, for example, velocity v1. And also we have many points that are closer to the axis of rotation, let's say. Let here in this place there will be some point v2, and this point will have already a velocity less compared to the velocity at the point v1. Why less? Let's break it down. If this disk is a solid, that is a solid body, then it is clear that when this object moves, all the points will rotate the same way. And that means that when you rotate by one angle or the other, one point has to travel along a path compared to the path that point 2 takes. And due to this, the velocities of these points will be different, because for the same time they travel different paths. And so you can describe the rotation of the same body, but with a value that changes for different points on the body, it's very inconvenient. So of course the question became, what parameters can be used to describe this motion? And naturally, the most convenient parameter in this case will be the parameter that is the same for all points of this object. And what is this parameter? Let's look carefully at the figure. The first one, of course, you guessed it, is the rotation angle. That is, how much of an angle this object rotates through over a period of time. Let's denote this angle by the letter θ. In physics, this quantity is denoted by the letter θ and is called angular displacement. The only measurement of this parameter is the angle which we measure in radians. So it is not a degree measure of angle, but it is the radian measure of angle. And so the ability to convert angles from degrees to radians will be important. Let's remember how to do that. Let me remind you that one is 1 radian. We have to multiply the number p by the angle we've chosen in degree measure and divide that by 180. And so we get an expression that will define this angle and translate it into radian measure. So for this value of the angle, you and I have defined the designation, defined the unit of measure, and now, of course, it is important to understand how the movement directly made by these objects is determined. How the angular displacement and, for example, the linear displacement of a given body are related. In this case, we can see that each point is moving on a circle, and our task is to find a formula that relates the length of this arc to the angular displacement of this body. In fact, there is such a formula, and let's recall it. I'll remind you of the formula that determines the length of the entire circle. And in this case, it's the product of 2 pi times the radius of that circle. As you and I have guessed, 2 pi here is nothing else than the angle of complete revolution. And in this case, it's clear that then the length of the entire circle is the angle of this turn on the radius of this circle. So from the special case, you and I can see there's a more general formula that will determine the length of the arc as the product of some angle on which this arc rests by the radius of the circle. Thus, we can easily find the path traveled by the body, i.e., the length of this arc, knowing the angle and the radius of this circle. So that was the first point that you and I have to label in this situation. Now, of course, it is important to remember a number of other quantities that will describe this motion. For example, a quantity that shows how long it takes for a given body to make one revolution. In this case, this quantity is called a period. Now we denote it by the letter T, and in order to calculate the time for one complete revolution, we have to divide the total time of rotation, that is how long it's been rotating, by the number of revolutions. As a result, we get a value that has the dimension of a second. That is, we got the time of one complete revolution. Well, and accordingly there is a value that is the inverse of this period. This value is called the speed of rotation and is defined as the inverse of the period. Here the unit of measure for this quantity is hertz, or a second minus the first degree, which is basically the same thing. So, in order to calculate the parameters of this motion, you and I need to understand how fast this body is rotating. And if we're going to calculate the paths traveled, we already know how to relate them to these angles. And now, of course, in order to determine how fast this object is moving, that is, how fast it is rotating, you and I can introduce another quantity that will determine how much this angle changes per unit time of this motion. In this case, we get a value called angular velocity. And this velocity is denoted by the letter omega. And it's basically the same as linear velocity, which is defined by the ratio of distance traveled to time. Here, this velocity is defined by the ratio of the perfect angle of displacement theta, but in this case, let's denote it as delta theta, if we have a difference between the final and initial value of this displacement. And we divide this by the time interval during which this displacement was made. In terms of dimensionality, we get that angular velocity is measured in radians per second. That's the only dimension we'll use in solving problems. So today we have studied a new type of motion and some quantities that characterize this motion. In the next lessons, we will continue our acquaintance with rotational motion and look at new parameters. See you in the next lessons. Goodbye.